How many folks do you think we'll get today?
I don't know if they're burnt out.
Burnt out? From what? Just looking at the sun for 1-2 hours? Think so? No one else is in that room? Okay, well then we'll get started. How was your spring break? Not long enough. I always say that.
I agree.
You guys do anything fun?
I went to Tecate,
Nice.
Mexico.
Yeah. That must be nice. What? Snowboarding? That's good. Where'd you go? Oh, nice. Okay. Alfred?
Went to the zoo
Okay. Okay. Saw some animals.
and the safari.
So far, you went to San Diego? Let's go. You want any more fun?
Not really.
Okay, that's fair. That happens. I went to New York and then I went to Iceland. So it's currently 8 p.m. for me. So I am tired. But we're gonna have a great day. And I'm gonna try and stay up as long as I can today so that I don't get jet lag. I didn't do any grading. Did you do any homework?
Yeah.
Okay, let's go, let's go. I'll announce this again on Monday or on Wednesday. But essentially, I think one of the things that people are maybe struggling with as far as turning things in is the idea, okay, you can just turn it in whenever. When really you kind of doing yourself a disservice, because if you leave it and then you leave it and then you leave it, you haven't actually engaged with the material. And so you're seeing new material in the pair programming that you're like totally unfamiliar with. So I'm not gonna give you grades because one of the point of that is to be flexible, right? But I think one thing that I'll do is, we've created these documents so I can give you feedback. And so what I'll do is just when something was due and it wasn't turned in without an excuse, I'll note that, right? And so then I can see whether or not you're staying on track, because I think that should be something that's rewarded. If you stay on track, you should look at that and be like, well, I was able to keep up with the material as it occurred. And it doesn't mean that everything's finished and everything looks perfect, but at least it was attempted, right? Like if every problem is attempted or started, good. I'll say, started or completed, right? Depending on how far you get in it. And then if it's late without an absence or without an excuse, I'll just say late. And then if it's excused, if you're like, listen, I got really sick or, my dog died or something, right? Something that's relevant, I'll say late with explanation. And that way we'll have sort of 4 ways of seeing how your progress is going throughout the rest of the semester. And I probably should have thought of that earlier. Sometimes these ideas don't necessarily come to you as they're occurring, but hopefully we can be a little flexible in the way that we approach our homework. Did you do anything fun, Andrew? Did you do anything fun for spring break?
Oh, like bike ride.
Hey, that's fun. That's cool. Okay. Cool. So everyone feels refreshed-ish? No, not refreshed at all?
You need more beer.
More beer?
They had free samples at the brewery in Tecate.
Oh yeah, that makes sense. That makes a lot of sense. And I bet it was great. I'm sure. You do anything fun for spring break? Yeah.
I went to Bakersfield.
Okay. Was that fun?
Yeah.
Nice. Just wanted to clarify, sometimes seeing family is not as fun as it should be. Okay, good. So today, I really want to, jump right back in with the idea of initial value problems and how they differ from boundary value problems. We're still going to be solving differential equations. I will notice the absence of names. So if you haven't presented twice, I'm gonna be pointing at you. If you have presented twice, like Andrew, you're fucking chilling. And then the other thing I want to point out is the code proposal. So I had a few people reach out to me with ideas of what they want to do. You should do that right now. So, take 5 or 10 minutes to really think about it after the presentation before we get into the problem of the day, and think about what might interest you. Because this is a back and forth conversation. It's not like you say it one time and I say, great, and then we never talk about it again. It's more like you say, I'm interested in this topic, and we try and find a problem that's going to be the right size for you. Because it's really easy to bite off way more than you can do. And then in some cases, you do something that is just too simple, right? You do something that's analytically solvable, right? Okay. So have that in the back of your mind as we're talking today about initial value problems. Once we finish the idea of initial value problems, we'll basically have all of the tools necessary to do almost all of the techniques that I talked about last Wednesday, perhaps? Yeah. So you should be able to do quite a bit. Anything that interests you of all of those topics that I put up. Okay. So do I have a brave volunteer for initial value problems? Not Andrew? Yeah? Alfred, let's go. All right, let's go to 9.3. All right. Anyone not see the eclipse today? No, don't tell me that. It's just not gonna happen again for many years.
Initial I see a differential. I see a double differential.
Is this your first time reading it?
Yes.
Okay, well then I'm not gonna have you present on it.
Six.
Okay, so traditionally what we want to do is we want to read the material before we arrive. There's 2 reasons for that. 1, because then you are following whoever the presenter is. And 2, because then when you go to do the pair programming, you're not spending that time at the beginning of class working on it, right? I get it, spring break, everyone's relaxed, you're wearing pink shirts, you're like still on vacation, just had too much Tecate, right? I get it, okay? I was in Iceland, we had vodka. That was super good. But as I mentioned earlier, real late for me. So if you're not engaged, then I'm gonna fall asleep. Okay, so you gotta be asking me questions. You gotta keep me on my toes. Is that fair? You're gonna let me fall asleep when you're all gonna leave. Okay, so let's talk about what we mean by initial value problems. So we've been talking about ODEs, ordinary differential equations, or PDEs, partial differential equations. And what they really mean, or they've tended to mean, is some relationship on one side between something that's changing as a result of something else, right? That's the equality. So if we were thinking about charge, on one side we say, this is how the potential field is changing on the right-hand side due to the presence or absence of charge. Does that make sense? You might have another one that you say, how does the position change? Well, that's due only to the forces on the object, right? So it's always comparing these relationships. Here, we're going to talk about a specific class of problem where you start at a known time or a known set of conditions, and you propagate it forward. So this is similar to something we've done before. What would that be similar to? You started at a given time and you let it evolve.
We did earlier the predator-prey models.
Predator-prey models, yeah, that's a great example, right? So you saw how foxes would expand and rabbits would decrease, and then they would switch because you run out of food for them. Another example?
The attractor.
The attractor, good, right? So we had the Lorentz attractor. Good. Anything more like basic physics? Yeah, projectile motion was a great one. You know where it is and you shoot it and you watch where it goes later. Anything else?
The comet orbit.
Comet orbit one, right? So these are all things where we know where it is initially and you let it evolve, right? So some of them can be solved with RK4. It's fairly straightforward. You have some coupled equations, you break them down, and then you solve them. I want you to have a look at this one here. This is called the diffusion equation. And I'm going to write it on the board what each of the sides mean. And we're going to see if this can be broken down simply. Okay. So on the left-hand side of 9.18, you have d phi dt. What does that mean in English? What? Yeah, the velocity of what? Whatever phi is, right? Yeah, some derivative of the velocity, right? So it's how is phi changing is the first way we think about it, right? Okay, and what is this other thing? So d, that's just a constant. And then what is this thing? D squared phi dx squared. What does that mean? Sure, there's a different way to think about it when it's the double derivative with respect to space. So the first derivative with respect to space we think of as the velocity, but if you think about it in terms of a graph, what would you call it? The slope, good. What's the second derivative tell you? The curvature. So this one tells you the curvature with respect to space. And this one tells you what we think of as essentially a velocity. How does it change with the change in time? And we should just get into the habit of kind of like seeing these, because if I take this, I can turn it into English, right? Kind of weird, but you know, experience helps. So this one says the rate at which phi changes is due to how curved it is at that location. Okay, so let me show you an example. Here's a graph. Okay, this line, let's say this is X, that's Y. Okay, and this line here is phi. What's going to happen to phi with time? Why? Right, so no curvature, so no change in phi. Okay, what about this? Good, how's it going to change? What do you mean increase?
From left to right as the position is changing?
Good, so over here, do I get any change?
No.
No, here do I get change?
Yeah.
Big change, right?
Yeah.
So this will start to move quickly. Over here, do I get change?
Yeah.
No, do I get change here?
Yeah.
Right. So as a whole, it's going to try and become this. This is the version of an equation we call the diffusion equation because it diffuses whatever you have out. If you start with sharp things, they become soft. Okay, so you start with something like a big bump, and maybe a second later, it looks like this. And then a few minutes later, it looks like that. And then 10 minutes later, it looks like that. Does that make sense? Okay, until it becomes totally flat. Good. So that's what we're going to solve today. And I'll leave it to you if you're very interested to try and do that with an RK4, but you want to solve two things at the same time here. One, you have the time changing, and two, you have something that is changing with the double derivative in space, right? So that double derivative in space we've addressed before. We did that with the Poisson equation. So we can use that same piece, right, to find out what the curvature looks like. We go up, side, subtract from the middle, right? And we know how to solve the right-hand side. The right-hand side is just Euler's equation, just step things forward in time, right? So that'd be the easiest way to do it. Now you could solve it with RK4 to step forward in time, but I don't think the first example that we do is gonna be that complicated, okay? So this will give you something called a space-time grid. You're thinking, wow, came back from spring break and now we're talking about space-time. No, don't worry, it's not special relativity. We're just taking a combination of a grid that looks like this right? 2D, but now we're going to move it through time, right? So it'll be a 3D grid. So at the beginning, it'll have some form, and then we move forward in time, and it looks like something else later. Okay? Okay. So there's a couple ways to do this. This one's fun. This is the forward time center space method. And it's just what you think it would be. Okay? Time is going to be propagated forward. Good. Okay. And the space derivatives are going to be centered derivatives. So we talked about those derivatives before, where you take one step forward and one step backwards in space, and we take the difference there. So here's how we're going to write our double derivative. That was the right-hand side. We walk one to the right, we walk one to the left, and we subtract where we are. Reasonable, right? And here's our time, right? d phi dt is just that. So that d is this constant here, and the grid spacing a squared goes on the bottom. So now all we have to do is find out how we expand this forward time. And in fact, we've done that before too. So we said that the derivative is basically equal to where we are now plus the derivative times h, right? So if we go back up, this is going to be, let me write this a different way. If I could write this piece here as f of x t, right? That's the derivative. Right? Okay. So then all we're doing here is we're saying, oops, where'd it go? We're saying, okay, the derivative at, sorry, the variable phi at a time t plus h is just what the original one was, plus h times that function f. Reasonable? Okay, so we haven't done anything groundbreaking. We haven't ruined anyone's minds, right? Maybe a few. Okay. So let's see what that actually looks like. Well, we just wrote out what this one was. So we're going to say, here's the x of, phi of x at t plus h is just the original plus all of this physical stuff from the curvature. Okay. And that's it. And then you step forward. Step, 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 step. Okay, so let's look at this in practice. Here's the heat equation. And this is a straightforward one. Let's imagine we stick a container, steel container, with hot water in it into a container of cold water. And the goal is to calculate the temperature profile of the steel from the cold water to the hot water. So initially, you can assume that it has some equal temperature, just the temperature of the steel. And then as you immerse it in the cold water, what do you expect to have happen? Temperature drops on the outside, right? Okay. But the inside water is still hot. So you're going to have to smoothly connect those two. Does that make sense? Not you, the computer will. Okay. So let's have a look at it. Here's the temperature equation. The same one as before, but now instead of d phi dt, it's dt dt. And we want to be careful when we're writing this up that we use the word temp, right? Because we want to, time will increase, but temp won't necessarily always increase. In some places, it'll go down. Okay. So here's what we have. We have the thickness of the steel. We have something about the diffusivity of the steel, how well it distributes heat. We're going to use 100 grid spacings, and we're going to use a really small time step. We have an epsilon because we want to make sure that we step, smoothly through the physics. The low temperature, the temperature of the water, the cold water, is 0. The temperature of the hot water is 50, and we're going to start the steel at 20 degrees in Celsius. Okay. And I want it to print out solutions at these time periods. Okay, so I'm going to highlight these as individual time periods, and then I'm going to add, I'm going to have the simulation end basically 1 second, or how much should I say? 1 e to the -4 time steps after 10. Okay. All right. So let's make some arrays. These are going to be just a linear array. I don't care about this direction in the steel. I only care about the transition from hot to cold, or sorry, from hot to cold. Okay. So here I'm going to say T0 is the hot part and Tn is the low part. So this will be my surface that's touching the hot water, and this will be my surface that's touching the cold water, and then everything else in between. See that beautiful slicing? Nice slicing, right? Okay, that's the mid. Mid being something different now. When I first started teaching, people didn't say mid like that. Okay, and we're gonna do two things. We're gonna apply this in the same way that we did with that previous one. We're gonna have something like T prime and T. So we're gonna solve T prime based on what T is, and these are temperatures. So the updated temperature is gonna be based on the previous temperature, and then we're gonna swap them like we did before. Now you have to really brush off those cobwebs, get that brain back working. But that's what we did before. We said the new temperatures are due to the old temperatures. And then once we calculated them all, we switched them, right? And then we did it again, okay? And this is how we create our arrays, how we set them all up. So here's the main loop. Let's start at t = 0. Start at time = 0. That's a reasonable thing to do. Here I have this constant, which is due to all of these constants. Just going to multiply them all together so that I don't have to put all of them into the equations. And this is going to be a while loop. But this is a different type of while loop than we've seen before. In the past, we've used while loops to sort of narrow in on the goodness of our answer. But this one here, what we're going to do is we're going to let time increase step by step by step until we get to t end. I personally wouldn't do it this way. I'd do a for loop, because as long as your time step isn't changing, you should know exactly how many times that is. But if you want to do it this way, you're welcome to. Okay. And here's the meat of the problem. Here's the hardest part of the problem, is coding this up. Okay. So I'm going to calculate the new values of temperature. I'm not going to ever update the edges. So I never update 0 and I never update n+1. I leave those as my fixed edges. And then what I do is I say my new temperature is due to my old temperature plus that constant. And then this is my centered space, right? So 1 to the right, 1 to the left, minus 2 times where I am, right? And then I take my fully updated arrays and I swap them. Whoop. And I increase T by 1. Cool, right? I may have said this before. If we haven't done this before, this is a great example of how to sort of fake an animation. So what you can do here is you can just say, well, I'm going to make plots at a given time. If the absolute difference between the current time and that time that I talked about earlier, so I wanted these times up here to print out. So if that difference is smaller than epsilon, make one plot, please. Right? And then you can change these numbers, these T1s, T2s, to be whatever you want. And it'll just plot one on top of the other, on top of the other, on top of the other, right? Until the simulation's done. Then I'm going to label it and I'm going to show it. And that'll give me my time evolution. You can be even more fancy with that. You could go in here, you could plot T, and you could do comma, label, and then you can give it a label, say like first plot or time equals this or whatever you want to do. This is how you move forward in time, right? So this is the Euler version of moving forward in time, because I simply take the original one plus what essentially is the velocity times time, right? To update it. You could do this with RK4, but we won't do it here. You'll notice as we do some more complicated equations that RK4 won't be the answer. And in fact, you'll find we'll have some discussions about what's called numerical stability. So for example, when we do something like waves on a string, we will break the computer because on one side we'll be solving 2 derivatives of time and the other will be solving 2 derivatives of space. And if we don't do it carefully, everything will blow up. Okay. Okay. So that will be a version of a numerical approximation that fails. So we try to approximate real physics on our computer and something gets lost along the way. This one is a lot safer. It's a good introductory experience to for time-centered space. So we'll use that here to propagate heat through an object. And then for the problem today, we are going to propagate heat through the Earth's surface due to the sun. Oh, okay, got someone interested. All right. So let's have a look here at what we're going to be doing. Let's see if I'm right. So 9.3 is the example. I think I just showed that. And 9.4 will be the pair program. Yeah, good. So let's first pull out 9.3, just the example problem, and see if we can code that up and see if we can understand how that problem works. But before we do that, I'd like you to take, the rest of this 5 minutes to, if you haven't already, send me what you're thinking about for your code proposal. Okay. And this is an ongoing conversation. So don't feel like once you've said it, you can't change your mind. You just need to start thinking about doing it because we only have 1, 2, 3, 4 weeks of class, which I believe counts as a month. That can't be right. That's got to be a lie. Okay. That's insane though, right? Doesn't it feel like it was like taking forever, and all of a sudden it's over? Okay, so we're going to cram your brains, fill them with knowledge, and then you're going to be like, wow, I'm really good at this computer stuff. Okay?
What do you want us to send?
Send it in an email. You can send it on Slack, anything that I can reference and start a conversation with you about. Okay.